Maybe today I'm gonna be talk about the induced drag because that seems to be the hardest part of the calculation, right? So doing the finding the power essentially requires you to multiply the total drag with speed, and finding the energy involves basically multiplying the total drag with distance. So both are pretty simple if you can figure out the total drag. And so far, total drag is just equal to the skin friction drag plus wave drag, which we said is negligible for the airlines flying at that speed, right? So I mean, they are designed to fly at a speed where wave drag is not a big factor yet, right? Okay, so wave drag, let's ignore it for now. And but you may have to start looking at it when you are redesigning the wing, right? I mean, when you redesign the airplane, its shape changes. Now you might have to redesign the wing such that wave drag is not a factor. Okay. Now, skin friction drag is easy to calculate. You just need to calculate the whole area and estimate the skin friction coefficient based on the Reynolds number. And you will see that at this Reynolds number, the skin friction drag is pretty flat as a function of the Reynolds number, right? So no matter if you base on the chord of the wing, the length of the fuselage, etc., the skin friction coefficient doesn't really change that much. Maybe it goes up and down by 10%, but not much more. All right, so skin friction drag is pretty easy to estimate if the required accuracy is like 10-20%. That leaves us with the induced drag. And the induced drag is actually what changes a lot when you place two aircrafts in the vicinity of each other. Last time we said we can use this a very simple method to calculate the induced drag. So if you have four vortices, right, one coming from the tip of each side of each aircraft, we can really split up each wing into multiple segments and look at what is going to be the downwash on the center of that element. So for example, if we can split the front aircraft into 4 segments, split the back aircraft also into 4 segments, we can use the formulas to compute how much downwash, right, is on each segment. And the downwash combined with the speed of the free stream allows you to calculate how much the lift vector is tilted backwards. And the backwards component of the lift vector is what makes induced drag. So today we're going to go into the software AVL, and the software AVL essentially does exactly that, but replaces a lot of the tedious calculations with computer programs. And that replacement allows you to not just split the wing into just the 4 segments, but potentially 8 or 16 segments. Okay, so here's what I'm going to show you. Okay, so if you install the AVL, did you install AVL on your computer successfully? Okay, that's good. So as long as it works, and you can also see there is a directory called the rungs. There has a lot of files, including a lot of .avl files. You see that? So for example, if you open just let's say wing.avl, you're gonna see how a simple wing is represented in AVL. So you have the Mach number and a bunch of flags that tells you the symmetry, symmetry flags, right? 0 means no, and the references in area, chord, and this is the span. Okay. And this is the reference locations for computing the moments. So this is basically a few numbers that's in the header of the AVL file. So and then it starts to define a surface that's a wing, right? So the wing basically has two sections in this case. And what we're going to do today is we are going to copy this file and duplicate the wing by placing an exactly the same wing, but a little bit behind of the existing wing. So let's copy the wing.avl to, let's say, toWings.avl. All right. And we are going to edit the toWings.avl. And what I'm going to do is I'm going to copy from the beginning of the surface to the very end. So basically, I have another surface that right now is exactly the same. And then let's go through the definition of the wing and see how we can move the wing to a little bit more downstream and also offset it a little bit from the center line. All right. So we don't need to change all of these. These are parameters that defines how, like, how do you split the wing into segments when you're computing the trailing vortices and also the downwash on the wing. So these are really basically it splits the wing into 8 chord-wide sections and 12 span-wide sections. So the span-wide sections are the span-wide sections we use to compute the downwashes. And the chord-wide section is you can think of it as the vortices we are thinking about when we are placing vortices in two-dimensional airfoils, right? So they basically, instead of having a single vortex, like placed at the quarter chord, it is actually placing 8 vortices along the chord, right? At every spanwise location. So if you look at this wing, this is really, there are 8 times 12 vortices, okay? And the Y duplicate is, so the symmetry location of the wing. So in the Y, so you know, like the coordinate system, we usually designate is X is in this direction, right? Y is in the spanwise direction, and the Z point upwards is in the opposite direction of gravity. All right. So a Y duplicate means the location of the center line of the wing. So the first thing we have to change is, let's offset Y by a little bit. How much do you want? By the way, the wing has a Y equal to 0 and 7.5. So the span is 15, right? So how much do you want to offset the Y, the center of the wing behind? 10. All right. Okay, good. And the angle, let's just keep it to be 2. So the section are basically, there are 2 sections. One is the root of the wing and one is the tip of the wing. So the leading edge, instead of x equal to 0, we want to place it far behind the front airplane, right? How many chords do you want to place it behind? It's not how many chords, how many spans, let's say.
5.
5 spans. Okay, let's try that. I don't know if the visualizations, let's do that anyway. So 5 spans would be 75, right? 1 span is 15. All right. I'm a little bit worried that we won't be able to see much, like with the 2 wings separated so large. But let's try it anyway. So Y leading edge, as we put the Y center line to be 10, right? The Y leading edge has to be 10. That's the root section. Okay, and let's keep everything like the Z chord, etc., to be the same. I mean, do you want to change the Z? Do you want to place the airplane behind to be above or below the front airplane?
Won't it like vary as it's flying? Like, doesn't it depend on like?
Above.
Above? How much?
Like in terms of chord lengths or?
Yeah, just to give me a number, right? Maybe 10, okay? Okay, so let's keep everything else to be the same. Oh, and the control, okay, so this is basically flap and aileron, so we have to give it a different name, like a flap B, aileron B, let's say. Okay, the second section is the tip. So if the original X is 75, because there is a slight sweep, so let's just keep the slight sweep, so 75.4, right, as the new XLE of the tip. And the Y, so instead of 7.5, now it's 17.5, right? Okay, and ZLE, there is also a slight dihedral, so instead of a 0.75, it's 10.75. Everything else stays the same, and the control flap B, aileron B. All right, so basically, the whole system has 2 flaps and the 2 ailerons. Yes?
Where do you get the AVL file for this?
It's in the runs directory. I mean, if you download it inside the package ESP, then probably didn't include the runs directory. So
I just went back to the recitation notes.
So just look at this instead of your screen. All right. So where are we so far? I think we modified the whole thing, right? Is there any other stuff I missed? Like, of course, we can also change a bunch of things. We can change the sweep, for example, make the leading edge instead of 75.4, we sweep it to 78.4, for example. That will make the back airplane sweep a little bit more. Now we run in the bin directory. We have the AVL, right? So that's the main interface, and we load the 2 wings, the file we just edited. So it should say like load the error opening file. I mean, it automatically appends .avl, so it reads it. Oh, actually, both of these surfaces are named the wings, so I think we should change the second one to, let's say, back wing. All right, okay. So AVL load 2 wings. Yeah, so we have a back wing, and it's duplicated as a back wing Y dupe. So it's the duplicated wing, and this is the front wing. Okay, and also duplicated. Mark is point. We can also change the Mach number if we wish. So for solid surfaces, these many strips and these many vortices, right? As we said, basically the vortices are placed on each chordwise location and on each span. Now we go to Opera, and the first thing you can do is plot the geometry, right? We have 1 airplane in front, 1 airplane in the back. All right, and for example, one of the things you can look at is to look at the so-called bonding legs. So if you do BO, BO actually, sorry, you can look at what is that? The trailing legs, TR. So that actually tells you what are the vortices, right, that comes out of the airplanes. Okay, and once you do execute the run and you go back to geometric plot, you can plot the loading. So the loading is the green little arrows. I mean, these 2 airplanes are so far apart that these are pretty hard to see. But if you change the view angle a little bit, for example 0, 0, that would actually give you a front view of these 2 airplanes. And now if you compute the Fn surface forces, it actually tells you what are the forces on the airplane. Yeah. Okay, so let's move the x axis maybe to 25 instead of 75 and 28. And let's see if we can load the two wings and run it. Oh, upper and run it. And look at the geometry in this case. So they are a lot closer. And let's look at the trailing legs to see. I don't know. Let's view it from above. So let's see, 90. Yeah, so okay, so we actually do see the trailing vortices overlap with the hind wing, but this is still not good enough, right? You theoretically, I mean, you should have this vortex actually go a lot more downstream of this wing in order to have the full effect of these trailing vortices on the back wing, right? Okay, but we should already see if we turn on the loading and make the view angle to be 0, 0, we should already see these loadings are not going to be exactly symmetric. Okay, so especially if you actually print the total forces on the screen, and you should be able to see that still see the CL to be the same for the back wing, but somehow the CL is not the same for the front wing. Did I flip over the order of the two wings? Oh yeah. So this is the front wing. Sorry, this is the front wing, and then the later on is the back wing. Okay, this is the back wing. All right. Okay, so load the two wings. And upper and x is round the case, compute the forces, and if you plot Fn, that's the surface forces. The forces are like this. So if you look at the back wing, the front wing has symmetric CL, right? On two sides of the wing, the CL is the same, but the back wing has different CL now. And the back wing on the outer side actually has a larger CL than the wing on the inner side, right? And now if you look at the CDI, the induced drag, you're going to see that the back wing on the outer side has a smaller induced drag than either the front wing or the back wing on the inner side. All right, so this would be actually a lot more. Let me actually go back and edit the file to just to make things more clear. Let's actually move the back wing, the Z location of the back wing actually onto the same plane. All right, so basically the two airplanes are gonna be on the same airplane. Load the two wings, X and Fn. Now if you look at the back wing, you should see the CL being very significantly non-symmetric, right? So the outer side now has a much larger CL than the inner side, and yeah, the CDI is also reduced by quite a bit. All right, any questions on this so far? Okay, and of course this is a case where the angle of attack is not very, the angle of attack is 0, right? And if you look at the lift coefficients, they are also very small. So let's actually make the lift coefficient a bit larger, more closer to a typical cruise case. So one of the things you do is you can change your alpha, and so it gives you a lot of options of how to change alpha. For example, you can change alpha such that the CL is equal to, let's say, 0.5. Okay, so that's okay. Then you're gonna see if you run it. So if you do alpha, if you see CL to be 0.5. What? Oh, C 0.5. Okay. Oh, right. Okay. So you can't see CL, you have to see C. Okay, then you run it. You're going to actually get an alpha, and just to make sure, if you look at the forces, it should actually get you much larger results, right? Okay, so I did not change my reference area. All right, so basically, I increased my wing by a lot, and I'm still having the same reference area. So the individual CL is not very high on this one. But anyway, so we can still start to look at the different. If you look at the geometric plot, and the particular turn on the cancel, turn on the forces loading, right? You should now see, okay, the distribution. Let's actually rotate it, V to be 0, 0. Okay, so that's actually not. That's pretty obvious, right? On the this is the back wing, and you see the loading on this is the starboard side of the airplane, right? Because we are looking from the front. So this side of the loading versus this side of the loading is very different, right? So the loading is pretty much uniform on most of the wing except for at the tip. But over here, the loading is high here and suddenly goes down over here, right? So that's where the tip vortex of the front wing is now affecting the distribution of downwash on the airplane behind. In particular, the vortex rotates like that way, right? So it creates an upwash just outside of the tip vortex and the downwash inside of the tip vortex. And the result of that is the angle of attack, right, for this portion of the wing is larger, right? It's made larger by the tip vortex. And angle of attack of this side of the wing is made smaller by the tip vortex. Not only the angle of attack changes, but the lift vector gets tilted, right? That's where the change in the induced drag comes from. And for this wing, it almost cancels out because the lift vector is actually get tilted in which direction for this part of the wing? Yes, forward, right? So that decreases your induced drag. But for this part of the wing, the lift vector get tilted backwards. So that increases your induced drag. While for this part of the wing, everything, all the induced drag goes up. So all the induced flow goes upward. So all the lift vector got tilted towards the nose of the wing, so the induced drag is actually smaller over here. You should see it to be more significant if you further change the case such that the Y location is not 10, but how much? If it's exactly one span, right? If it's 15, let's see how that affects things. So that'll be 22. Is it 22.5? Yeah. Is that right? Yes, 22.5. Okay. All right. So if you do that, load the two wings and upper X. Okay, so let's put CL. Change alpha so that CL is equal to, let's make it 1 so that the individual faces, I forgot to change the reference area again. Run it and do a geometric plot. Oops, I forgot to change. I forgot to change the Y symmetric. Okay, so Y duplicate should be also 15, right? Yeah, okay. So upper alpha C1, run it, geometric plot. Okay, now that's what we want it to be. So we want to plot loading, and you see like the whole thing, right? It gets the whole left wing gets a lot bigger lift. So let's view it from an angle of 0, 0, right? So you can see the whole port side wing of the airplane behind. Now it's getting higher lift. If you compute the forces, of course the lift on the duplicated back wing is now a lot higher, and look at the induced drag, right? I mean, both induced drag are reduced, and the side of the wing that's closer to the tip vortex has the induced drag reduced by more than 50%, right? Okay, so this is a way you can calculate like the whole induced drag of the formation flight. And I need to look into how do you extend. Okay, so I need to look at first of all. Actually, let's first test. Is it just a visualization artifacts? Does AVL actually extends the tip vortex far downstream, or it actually doesn't? So let's actually copy this, and let's copy this and just paste this over here for reference, and let's actually move the back wing in the z direction. Just to put 100 over here, okay, 100 and something, and see if the induced drag reduction is still there. If AVL doesn't extend the vortices that long, that it would completely negate the induced drag reduction, right? If it does account for that, then there should be induced drag reduction. Load 2 wings, and upper, and we change alpha so that CL is equal to 1. We run it, and we plot the forces. Okay, the induced drag reduction is there, right? So we don't have to worry about the extension, right? So if we do a geometric plot, we should see, yeah, the back airplane is so far behind, but the induced drag reduction is still there, right? So here we have 0.53 for the 0.0053 for the front airplane. So that's a little bit more than what we had before, because the airplanes are so far apart that the effect of the airplane behind now have basically zero effect, right, on the airplane flying in front. While when they are still not that far apart, the tip vortices from the airplane behind still has a non-zero effect on the airplane in front. Now they are so far apart that the induced drag reduction coming from the airplane behind is basically zero. And the induced drag reduction on the airplane behind, okay, 44 and 21, 4421 is still the same. All right, so that's a good sign. So AVL actually tracks the tip vortices to infinity, even though when you plot it like a TR, it doesn't show so. All right, okay. So that's how you compute induced drags, and you can play with all kinds of parameters like the location of the wings, how far you are apart, is it higher, lower, etc., to make things a bit different. Oh, one thing I forgot to mention. So if you look at the forces, the two airplanes has the two sides of the wings have different CL, right? What does that mean for the airplane flying behind? It's going to roll, right? It's going to roll towards, it's going to roll away from the front airplane because the wing closer to it has a higher lift. So one thing you can do is to change the ailerons, right? I mean, in practice, you would deflect the ailerons to counter the roll moment, and that's something you can do. For example, here we can change the back aileron. We can change the D4, right? And so that well, you can compute how much roll moment you want, but let's just make it D4 equal to 1 and recompute. So, oh, did I make it worse? Yes, I did make it worse. So the we should deflect the ailerons in the opposite direction. So D4 minus 1, Fn. Right, now the CL are closer to each other, right? So this would be a case where like you would actually look at the total induced drag. In this case, because the way I'm deflecting the aileron, so the wing closer to the trailing edge vortex of the front airplane actually gets less lift, right? That less lift further decrease the basically the less lift decreased how much like trailing edge vortex that wingtip has, and that actually combined with the less lift further decreased how much induced drag it has. While the other wing, because now it has a higher lift, stronger trailing edge vortex, tip vortex, and the induced drag increases. But overall, you still get plenty of induced drag reduction from the whole system. All right. Good.
Induced drag on each side of the wing.
Oh yeah, that's the job of the vertical tail, right? So if you account for the detailed flight, I mean, if you fly a glider, by the way, like I don't know if you like do flight simulations and things like that, like the Microsoft Flight Simulator just released 2 gliders, and you can try fly them. So if you actually fly a glider, somebody is towing you, and if you want to offset a little bit on one side, the towing force, right, is also a vector. If you are flying on one side, like what do you have to do if you want to offset on one side? You actually have to bank a little bit, right, so that the thrust force coming from the tow line is going in. Let's say if you want to offset to the left, right, then the tow line is going to be tow you towards the right. So you have to bank left a little bit to offset that. But like, if the distance between the 2 airplanes are long, then how much the tilting of the thrust vector coming from the tow is so small that the amount of bank you have is almost negligible. And to counter the difference in yaw due to the different induced drag, you have to push your rudder a little bit. Again, let's just ignore these small things for now. I mean, you can calculate them, but they'll end up to be pretty small.